How do you do math on a coin flip or a defective machine part? In probability, real-world events are qualitative: heads, tails, rain, or shine. You cannot plug heads into an equation or multiply a defective product by 5. We define a random variable, capital X, as a deterministic mapping function. It assigns every abstract outcome a usable position on the real number line. The function takes a qualitative event, like 2 heads, and assigns it a specific numerical value, such as 2. This architecture allows us to express physical events as numerical distributions. We can graph their specific densities, accumulate their total likelihoods, and compute their averages and spreads. Modern data science and statistical computing rely on this conversion of qualitative chaos into predictable numerical objects. The notation distinguishes the rule from the result. A capital X represents the random variable itself, the rule, while a lowercase x represents a specific numerical value it might equal after an experiment occurs. Once an outcome is mapped to a number, the mathematical path splits into 2 distinct categories based on the type of output the variable produces. Discrete random variables take a countable set of distinct values with spaces between them, like rolling dice. Continuous variables take any value within an uncountable interval, like height or wait time, where the scale is infinitely divisible. This distinction dictates the math. Discrete variables use summation to find probabilities, while continuous variables require calculus and integration. Categorizing the variable correctly is the prerequisite for all subsequent operations. For a discrete variable, the probability mass function, or P of x, outputs the exact probability of a specific numerical realization. This chart shows the PMF for rolling 2 dice. The spike at 7 returns exactly 6 out of 36. In any PMF, individual probabilities are non-negative, and the sum of all spikes must equal exactly 1. Continuous variables use the probability density function, or f of x. This continuous PDF is defined by the function 2x, bounded between 0 and 1. Note that f of x outputs density, not probability, so the y-axis can safely reach a value of 2. The only strict constraint is that the total area under the curve equals exactly 1. At any specific point, like exactly 0.5, the probability is 0 because a one-dimensional line has no area. True probability for a continuous variable only exists over an interval. We calculate the area between 2 points using an integral. Confusing density with probability will invalidate a continuous model before the analysis begins. We can simplify interval calculations using the cumulative distribution function, or f of x. This function measures the probability that x is less than or equal to a specific value. The logic of the CDF applies identically to both discrete and continuous variables. On top, the discrete dice CDF is a step function, jumping at each outcome to accumulate probability. Below, the continuous PDF transforms into a smooth CDF curve, constantly accumulating area bounded strictly between 0 and 1. Every valid CDF is non-decreasing. In the continuous case, the derivative of the CDF returns the original PDF. This provides a consistent mechanism to compute tail risks and percentiles regardless of the underlying distribution's shape. Instead of analyzing full curves, we often use summary statistics, beginning with the expectation, or E of x. The expectation is the probability-weighted center of mass. It represents the long-run average value of x over many repeated trials. We model this as a balancing point. Imagine a game with a 20% chance to win $10, 50% for 0, and 30% to lose 5. Summing each payout by its probability settles the fulcrum at 50 cents. 50 cents is the long-run average, even though it is not a value you can actually win in a single round of the game. The law of the unconscious statistician, or LOTUS, allows us to compute the expected value of a transformed variable using the original distribution without deriving a new one. This leads to the linearity of expectation. E of ax plus b is simply a times the expectation of x plus b. This property holds even when variables are dependent. These properties allow us to evaluate complex transformations without recalculating the underlying mathematical structure. The second major summary is variance, or sigma squared. If expectation is the center, variance measures the average squared distance of the variable from that center. We often use a shortcut formula, the expected value of x squared minus the square of the expected value. For our payout game, the variance is 27.25. Unlike expectation, variance is nonlinear. If you scale a variable by a factor a, its variance increases by a squared. We take the square root of variance to find the standard deviation, which returns the measurement of spread to the original units of x. We use the mean and standard deviation to standardize random variables. This process shifts any distribution so its mean is 0 and its variance is 1. To calculate a z-score, we subtract the mean from the variable and divide by the standard deviation, enforcing a uniform scale. Standardization enables fair comparisons across disparate datasets and fulfills the structural requirements for the limit theorems used in statistical inference. This is the architectural pipeline. Outcomes map to numbers, numbers map to functional shapes, and those shapes distill into isolated parameters. This logic provides the framework for building predictive models, risk analyses, and simulations. With this framework established, we can classify the specific named distributions, including Bernoulli, binomial, and Poisson models. Mastering these rules provides the vocabulary and logic necessary for applied statistical theory.